All right, working on the waves review guide here. I'm just going to talk through the vocab here at the beginning. So wave is a disturbance that carries energy through matter or space. Speed depends on the medium an object is traveling through, such as solid, liquid, or gas. Closer the particles are together, in theory, the faster the wave will move. Most waves are caused by vibration. Letter T is variable for waves period. You should know all variables and their units as well. Highest point of a wave is crest, lowest point trough. Height is the amplitude. Distance between two similar points of wave is wavelength. The period is the time for a wavelength to pass, and frequency is how many pass in a given amount of time. For us, it's per second. What is the equation for speed or velocity of a wave? That is equal to frequency times lambda, and that's how you make your triangle. Okay? Greek letter we use for wavelength is lambda. Frequency is equal to 1 divided by period. Period is also 1 divided by frequency. We'll come back to those triangles later. So wavelength is letter C here, so that's letter C. Crest is the top, that would be letter A. Trough is letter B. And amplitude is maximum displacement, that would be letter D. This type of wave, as the wave is moving left-right, particles are moving up and down, that is perpendicular, so that's transverse. Is light or sound this type of wave? That would be light. At what point is the maximum vibration? That would actually be 2 points, crest and trough. So it would be A and B would be maximum. No vibration? This one's a little bit tricky. That's actually like right here, okay, right at that point in time. There's no vibration happening. What type of waves need a medium? Sorry, that'd be mechanical waves. Electromagnetic do not. What type of wave moves perpendicular? That's transverse. Sound is a longitudinal wave. Football game, it moves from left to right. People go up and down. Oh, sorry, that would be transverse. What type of wave do not need a medium? That would be electromagnetic. So comparing, contrasting those two types of waves. Light is what kind of wave? Light is an electromagnetic wave. Hopefully you don't need a calculator to do that. Combination of two or more waves is interference. Resonance is a tendency of an object divided at a natural specific frequency. And I gave good and bad here would be pushing on a swing. Right as that person starts to move forward, you give them a push and they move faster. Bad would be if glass shatters. It starts to vibrate and then it shatters at a specific frequency. So this is the Doppler effect, 27 to 28. So remember, if I'm standing right here and a car is driving towards me, the wavelength starts to get closer and closer together. I'm trying to do my best here, so it's moving up and down really fast. The amplitude should be the same all the way through. Let me actually redo that so you can see. Okay, so object has really spread apart wavelength, and then it starts to get closer and closer and closer and closer and closer as it moves toward me. Then it moves away, starting close and then getting really spread out again. Okay, so amplitude is the same all the way through, but the wavelength gets shorter and shorter. So that means the frequency gets higher, meaning its pitch gets higher as it moves towards you, and going away from you, it gets lower. Two instances you observe this effect, you could say like a car driving by, car, or I'm going to type actually. It'll be easier. So I'm going to say car driving by. And you can hear that, such as its engine or the exhaust. Or another example would be like when you hear people yelling on a or people yelling on a roller coaster. As they pass you, it gets higher pitched and then lower pitched. So down here we got a longitudinal wave. I'm going to go back to the draw part. Wavelength would be letter A, would be wavelength. Compression would be letter B, and rarefaction would be letter C. Okay, what type of wave is shown above? That would be longitudinal. Is lighter sound this type of wave? That'd be sound. Maximum vibration, this would be like crest and trough. It's actually 2 points. It's B and C. Okay. It's stretched from normal. You can imagine like right in the middle of B and C, so right about here is the normal spread. The compression and the extension of the longitudinal wave, or the compression and the rarefaction, both represent maximum displacement from normal. When the crests of two waves meet, crest meeting is called constructive. It gets bigger. Crest and trough is destructive. Okay. Now down here, I'm going to need my frequency and period triangle. So frequency, that's a terrible F, period 1. Okay, so remember, whatever variable I'm solving for, I just try to cover it up, cover up the t. It gives me 1 over f. Okay, so in this case, period is equal to 1 divided by frequency, which is equal to 1 divided by 400 hertz, which, taking out my calculator, 1 divided by 400 is equal to 0.0025. Since it's period, it's seconds. Okay, so it gives you, which is the frequency of 400 hertz. It's my given. What's the period of this wave? That's t. Okay, same thing if I want frequency. So notice that it gives you a wave of 0.0039 seconds. That's the period. Okay, so f is 1 divided by t. So in this case, frequency is equal to 1 divided by 0.0039 seconds, which is equal to 256 hertz. I got another one here I'm solving for period. So I'm just going to copy and paste this down here and change some things. So period is 1 divided by frequency again. This time it's 1 divided by 78 hertz. And 1 divided by 78 is equal to 0.013 seconds. So notice lower frequency between these two, and the periods are different as well. Shorter period, higher frequency. So here, now this is another triangle that I am going to have to be able to make. So realizing here that wave speed is equal to frequency times wavelength. Okay. So now I can type here. So a certain wave has a wavelength of 3 meters. Got it right there. Wavelength 3 meters. Frequency of 125 hertz. What is the wave speed? Wave speed covered up is equal to frequency times the wavelength. So this is equal to frequency times wavelength, which is equal to frequency 125 hertz times 3.0 meters gives me 375, and it's wave speed, so units are meters per second. Okay. Here, sound moves through the air at a speed of 343 meters per second. That's true. If the frequency of this sound wave is 20 hertz, what is the wavelength? So cover up wavelength, it's v divided by f. V divided by f, which is equal to 343 meters per second divided by 20 hertz, which is equal to 343 divided by 20, 17.2 meters. Okay, lastly, here number 41, I am solving for frequency, which is equal to wave speed divided by wavelength, v divided by lambda. So it's v divided by lambda, which is equal to 100 meters per second divided by 2.0 meters, which is equal to 50 hertz. all using that triangle here. So label the following. You got highest energy. So the way that I usually would go about doing this one is notice it gives you wavelength here. Okay, so bigger number, longest wavelength, shortest wavelength. Okay, so that one should hopefully be pretty straightforward. Highest energy, you can think about it two ways. You know, you got your color spectrum, you got violet on this side. Notice this one's different than some of the others. It can be written either way. Depends on which direction you have it. Gamma rays are my highest energy electromagnetic wave. Radio waves, such as AM, are my lowest energy. Or I could look at the colors, violet and red, and know lowest to highest energy as well that way. Now, the hardest one then is with frequency. So think about frequency as being how close together the waves are, right? So the shorter the wavelength, the higher the frequency. Also, think about you looked at two different waves like this. Let's say you had a wave that looked like this. Sorry, give me a second here. So you had a wave that looks like this. Okay. And you had a wave that looks like this. This one's going to make more contact with you, short wavelength, but the frequency is higher, more contact, more energy. So that's one way you could think about that. So based on the information above, as wavelength goes up, wavelength's going up this way, what happens to energy? Energy goes down. As wavelength goes up, what happens to frequency? Frequency also goes down. And as frequency goes up, what happens to energy? It also goes up. So that's a pretty good review. If you have any questions, let me know.